So let's look at glycolysis, which is the first phase of cellular respiration. And glycolysis happens both in aerobic and anaerobic organisms. It actually also occurs in organisms that perform fermentation. Glycolysis, as the term suggests, glyco is glucose, lysis is breakdown. So breaking down of glucose is glycolysis. And this breakdown actually produces energy that we're going to use, that the cell is going to use for performing work or to perform certain functions. And this is done by oxidizing glucose to pyruvate. We have already talked about oxidation and reduction reactions. So this is an oxidation reaction where glucose is getting oxidized to form pyruvate. So glycolysis is splitting of sugar. It breaks down glucose into two molecules of pyruvate. So glucose is a 6-carbon compound and it breaks down into 3-carbon compounds, which is pyruvate. And glycolysis, it occurs in the cytoplasm. The second phase, which is citric acid cycle, the components of glycolysis, the pyruvate, then moves into mitochondria, and citric acid cycle happens in the mitochondria. These processes do not need energy. The final process is the one that needs energy. So these processes do not need oxygen. The final process needs oxygen. So glycolysis basically does not need oxygen. And glycolysis, the process itself, is broken down into two phases. You have an energy investment phase and an energy payoff phase. So basically it's almost like a business. So for you to reap benefits or profits from a business, you have to invest in that business initially. So glycolysis is similar. You invest a little bit of ATP, which is the energy in our cells. So you invest a little bit of that ATP to get a lot of ATP at the end of the cellular respiration process. So within this process, glycolysis, glucose is forming pyruvate. 2 ATPs are being provided to the system and it produces 4 ATPs just within this glycolysis process. So the net gain of ATPs is 4 minus 2, which is 2. So let's look at the process really quick. So the first molecule glucose, or the first compound glucose, is taking up a phosphate from ATP. So this ATP is breaking down into ADP and releasing a phosphate. And that phosphate is attached over here on the 6th carbon. So if you see, it's 1, 2, 3, 4, 5, 6. So on the 6th carbon, you see the phosphate being added. And for this process, you need hexokinase enzyme. And this new product is now called glucose 6-phosphate because the phosphate is on the 6th carbon. Then the next step is the conversion of glucose into fructose. Glucose and fructose are isomers. So you just convert glucose to fructose. And the enzyme involved in this process is phosphoglucoisomerase. And you have fructose 6-phosphate. Again, it's 1, 2, 3, 4, 5, 6. It's still on the 6th carbon. So you have fructose 6-phosphate. The fructose 6-phosphate then takes in another phosphate. So another ATP is getting broken down into ADP, and that phosphate now binds on to the next carbon, or the first carbon I should say, forming fructose 1,6-bisphosphate. So this is the first carbon, this is the 6th carbon, 2, 3, 4 and 5. So this is fructose 1,6-bisphosphate. This compound here then, with the help of aldolase, breaks down into 2 3-carbon molecules. You have dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. This glyceraldehyde 3-phosphate compound is extremely important, guys. We're going to look at this again and again later on in gluconeogenesis and other processes. So this is a very important compound. Now, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, they are isomers, so you can interconvert them. And most of the time in glycolysis, it's the glyceraldehyde 3-phosphate that is used in the process. So DHAP is converted into glyceraldehyde 3-phosphate. So now you have 2 compounds or 2 molecules of glyceraldehyde 3-phosphate over here. This glyceraldehyde 3-phosphate then converts into 1,3-bisphosphoglycerate. So let's look at that process. So there is a phosphate on 1 and a phosphate on 3. So you have 1,3-bisphosphoglycerate, and the 2 molecules of 1,3-bisphosphoglycerate are produced. And this then gets converted into 3-phosphoglycerate, and this is where the ATP production happens. So you have 2 phosphates over here. 1 phosphate is still continued while this other phosphate is released, and this phosphate that got released adds on to ADP to make ATP. Since we have 2 1,3-bisphosphoglycerate, 2 phosphates will get released, so you have 2 ADPs that form 2 ATPs. The 3-phosphoglycerate then forms 2-phosphoglycerate, where the phosphate from the 3rd carbon moves to the 2nd carbon. Okay, so this switch is just a glyceromutase or enzyme switch, where the phosphate from here is getting moved to the 2nd carbon. So you have 2-phosphoglycerate. Now from this compound here, the OH and the H, they combine to form water, and there is a double bond produced over here, making it phosphoenol pyruvate with the phosphate still on the 2nd carbon. So you have phosphoenol pyruvate over here. Now this last compound, phosphoenol pyruvate, then releases this phosphate and forms pyruvate. So again, you have 2 phosphoenol pyruvates. So 2 phosphates add on to 2 ADPs to produce 2 ATPs. So if you see in our previous slide, we produced 2 ATPs here. And then on this slide again, we produced 2 ATPs. So our gross ATP production is 4. And we already used 2 ATPs in the beginning. So we have a net of 2 ATPs. Okay, so that's the glycolysis process, which happens in the cytoplasm without requiring oxygen. The starting reactant is glucose. The end product is pyruvate. 1 glucose molecule produces 2 pyruvate molecules. And in the process, we are using 2 ATPs, but we are producing 4 ATPs.